So fourth block, you need to go to your 2122 notes handout to the page that we started on yesterday, talking about this different definition, limit definition of a derivative, specifically that can be kind of helpful when we're only interested in this one point C. So instead of shrinking the distance between to be 0, we still are doing that, but instead of letting the limit go to 0, we let the limit when we're looking at x going to c. Instead of h, instead of this distance going to 0, we look at the limit as we let x approach c. And so we did that yesterday together, looking at the new limit definition of a derivative example and showing that in our particular example, the right and left hand limits didn't match up, and so therefore the derivative does not exist. Well, then we skipped yesterday because you guys were kind of burning out on me. We skipped yesterday going back and looking at the definition from a couple of days ago. That still applies. So here's what that would look like. So if I'm going to, again, think about f of x as being absolute value x minus 3, and we're not going to write out all of it, but that definition was that f prime of x would be the limit, and most of you like the h's, so as h goes to 0, of f of x plus h minus f of x all over h. Well, then we could do the same kind of principle as far as plugging in the number we're interested in. We could replace that x, then replace this x, then replace this x. So if we are interested in f prime of 3, then that would be the limit as h goes to 0 of f of 3 plus h minus f of 3. But we already found out yesterday f of 3 was 0 all over h. Because back up here, f of 3 equals absolute value of 3 minus 3, which is 0. Okay, so this turns into the limit as h goes to 0 of just f of 3 plus h all over h. And we would want to look at the different one-sided limits. So we'd want to look at the limit as h goes to 0 from the right, and then we'd want to come down and look at the limit as h goes to 0 from the left. But f of 3 plus h means you're coming up here and you're replacing this x with 3 plus h. So it would be the absolute value of 3 plus h and then minus 3. That's f of 3 plus h. And then that would all be over h. Well, if you clean that up, that's the limit as h goes to 0 from the right of, well, those 3's are going to cancel. So now you're left with absolute value h over h. And that's a graph from chapter 1. Up at 0, 1 going to the right, down at 0, negative 1 going to the left. You're looking at the limit as you approach 0 from the right. It's up here. That answer's 1. You can do all the work down here for the bottom part, come up with that answer being negative 1. They don't equal, and so therefore f prime of 3 does not exist, just like it didn't exist when we worked on the new limit definition. So you just need to be aware that the day 1 limit definition, that's used most of the time if we're talking about just a general formula that we want to get out for the derivative that's going to work at any point we want. And then sometimes when we switch over to having just a single point that we're interested in, like the c value, then sometimes the second definition is kind of helpful. But you can do it with either one, and AP is not going to care. And if you flip the page back again, I can work this example out. I don't know if I'll have time to do it in the videos I'm making tonight, but this is an AP example from 2009, an actual test that they used, and here's a function and then a description that they give you. But notice they're asking, is f differentiable? Hold on for a second. Is f differentiable at 0? And then you've got to use a definition specifically with one-sided limits to justify your answer. So they're going to make you prove it to them. And if you're not able to prove it with one-sided limits, then you're not going to get your credit. Now, which set of one-sided limits you want to do is up to you. If you want to try to do it with the day 1 definition that we already used and then plug in the number, okay, great. And if you want to do it with the new definition that we used, that's okay too. Okay, if I have time, I'll record a separate video and I'll title it that it's the 2009 number 3B example. Okay, then that's all that you need. Oh, no, never mind, to catch up. No, we skipped something else too. Okay, so we talked about places where the derivative didn't exist, and it doesn't exist at corners and at cusps, and cusps are just corners, but they're rounded as you're coming in. And we showed some examples of why. Like we showed this one with the limit definition. We've just been working on it. And then we took a look at an animation for this one. But in both cases, the issue is the slope from the left and the slope from the right are not matching up. And so since they're not matching up, you don't have a derivative there. Then we looked at a vertical tangent. So for this split second right here, it's straight up and down. And so a straight up and down line has undefined slope. So therefore, then the derivative is undefined. I'm going to go ahead and get rid of these question numbers. And then we also talked about anytime you have a discontinuity. And this can be kind of deceiving because it can look like the discontinuity, that the slopes are matching. And while that may be true, that's great. You don't have a derivative if you have a discontinuity, ever. Okay. Then the last part that we missed was going over this theorem that's an if-then statement. And we talked in chapter 1 about if-then statements. If-then statements mean if you have all of the first piece of information before the then they flow one directionally and you're guaranteed the then, the last part. Sometimes kids like it to kind of organize it a little bit differently, so I made a chart. If it helps you, great. If it doesn't, no big deal. One of your essential questions, though, is coming up with a way that you can remember all this information. So this first step is just literally translating the if-then statement. If it's differentiable at a point, if you can take the derivative at a point, then you are guaranteed that it's continuous at that point. Going backwards, you're not sure. I would pause for a second if I were you, and I want you to try to think of the answer to this question. Can you think of a function that is continuous but is not differentiable? So continuous somewhere, but at that same spot, not differentiable. You can pause and kind of look back through notes and think of something. Hopefully you can come up with examples, your absolute value sharp corner, and then also your cusp sharp corner. Those are continuous. They have a value right here and right here, but they are not differentiable. So it is not always true that you can go backwards. Then something that is always true with if-thens. If you take the if-then and you put a not in front of both of the parts, then instead of it working with the forward direction, it works with the backward direction. So we can guarantee you that if you are not continuous at that point, that you are not differentiable at that point. That's always going to be true. So you want to make sure you know the directions that are always true. Should be a double. Okay. So that's what you missed yesterday as far as not getting caught up, not finishing everything up. So then that's it for this video, and you can rejoin to finish everything else.